Picture this. You've got a brand new computer, right? And it's packing a central processing unit, a CPU, with a blistering clock speed of 3 gigahertz or more. That absolute brain of a chip is literally capable of executing billions of instructions every single second. Yet when you click to open up a heavy application or load a massive file, you still find yourself sitting there, just watching a spinning wheel. So why does a processor that incredibly fast end up waiting around? Well, the answer lies in a hardware bottleneck we call latency. Your hyper-fast CPU is basically forced to twiddle its thumbs while it waits for data to travel from much slower components. So what exactly is primary storage in a computer, and how does it solve this massive problem? Let's get into it.
Welcome to This Explainer. Today, we are diving straight into the ultimate solution to that CPU bottleneck, the incredibly high-speed world of primary memory. We're going to uncover exactly how your computer's internal architecture bridges that massive speed gap between its hyper-fast processing brain and its huge, but kind of sluggish, permanent storage vaults. Here is our roadmap for today. First, defining primary memory. Second, why primary memory is fast. Third, RAM and ROM explained. Fourth, the magic of cache. And finally, primary versus secondary storage. Okay, let's jump right into part 1, defining primary memory. The absolute easiest way to think about primary memory, which you'll also hear called main memory, is as your computer's active working desk. The core function of this primary storage is to hold the exact temporary data and program instructions that the CPU needs to get its hands on right now. The big defining characteristic here is that the CPU can access these memory addresses directly. But, and this is a big but, it's generally volatile. That means the absolute second your computer loses power or gets turned off, everything sitting on that working desk gets completely wiped clean. It is built strictly for blazing speed and temporary use, definitely not for permanently archiving your files. Moving on to part 2, why primary memory is fast. Now, you might be wondering exactly why this primary memory is so incredibly fast. Well, it basically boils down to a few major structural advantages. First off, because it's wired directly to the CPU, data doesn't have to navigate a maze of complex input/output channels. Second, it's built using advanced semiconductor technology with absolutely zero moving physical parts. Just think about older mechanical hard drives for a second. They literally have to wait for a physical platter to spin up and a mechanical arm to physically move into place. That's a process measured in agonizingly slow milliseconds. Primary memory, on the other hand, operates purely at the electronic level. We're talking nanoseconds here. It works really hard to keep pace with the CPU's own clock speed, completely bypassing those slower system bus speeds that drag down the rest of the motherboard. All right, let's hit part 3, RAM and ROM explained. So the crucial takeaway here is the stark contrast between these two types of primary storage. RAM, or random access memory, is that flexible, volatile working desk we were just talking about. It gives you incredibly fast read and write access, but remember, the data is strictly temporary. ROM, or read-only memory, is an entirely different beast. It is non-volatile, which means it holds onto its data even when someone pulls the plug. ROM acts as the permanent structural memory of your system. It holds those absolutely critical, unalterable instructions needed just to wake the computer up, stuff like the BIOS, way before your operating system even thinks about loading. Now, if we zoom in a bit closer on RAM, it actually splits into a few specialized types depending on the circuitry. DRAM, or dynamic RAM, makes up the vast bulk of your computer's main memory. It stores data using these microscopic capacitors. But here's the crazy catch. Those tiny capacitors constantly leak electricity. They are literally like microscopic buckets with holes in the bottom. Because of that, they have to be refreshed thousands of times every single second just to retain their data, and that refreshing process takes a tiny fraction of time. Then you've got SRAM, or static RAM. This uses a totally different circuit design called flip-flops. It doesn't need to be constantly refreshed, making it significantly faster. But it's also way more expensive and holds less data. And finally, there's VRAM. This is essentially specialized RAM heavily optimized for the massive parallel processing demands of rendering all those complex graphics on your video card. And this next part brilliantly shows how ROM has evolved over the years. Back in the day, ROM was strictly permanent, literally burned into the chip at the factory. But then PROM came along, which let a user program it exactly once. After that was a pretty wild leap. EEPROM. Get this. To erase the data on an EEPROM chip, you couldn't just hit a delete key. No, you actually had to pull the physical chip out of the board and blast it with intense ultraviolet light. Thankfully, today we use EEPROM, which stands for Electrically Erasable Programmable ROM. This lets us conveniently rewrite data using simple electrical signals. It's exactly this technology that lets your computer update its core system firmware without you having to go dig out a UV flashlight.
Okay, on to part 4, the magic of cache.
You can think of cache memory as the ultimate VIP section for your data. You see, even standard RAM isn't quite fast enough to keep a cutting-edge processor perfectly fed with data. So, hardware engineers take a tiny bit of that super-fast, highly expensive SRAM we just talked about, and they embed it directly onto the CPU itself. It acts as an ultra-fast buffer, holding only the very specific data and instructions that the CPU accesses the most. When the CPU looks for data and finds it waiting right there, it's called a cache hit, and it saves a massive amount of time. So when we talk about primary storage, we are really talking about these 3 main pillars: RAM, ROM, and this incredibly fast cache.
There's a really fantastic analogy here to make this whole abstract hardware concept instantly relatable. Imagine your CPU is a librarian, right? And the data it needs to process are the books. Now, if that librarian has to walk out into the vast main library to track down a book every single time someone asks for it, things are going to slow to an absolute crawl. So what does a smart librarian actually do? Well, they keep a small dedicated shelf right next to their desk stacked with the most popular, frequently requested books. That is your level 1 cache. When a request comes in, the CPU checks that small, immediate shelf first. If the book isn't there, it checks the slightly larger bookshelf just behind the desk. That's your level 2 cache. Only if the book is totally missing from those convenient shelves does the librarian finally sigh, get up, and walk down the incredibly long, slow aisles of the main library. That main library represents your system RAM. By stacking multiple small caches, the CPU saves just unbelievable amounts of time that would otherwise be wasted searching through the larger memory banks. Finally, let's wrap up with part 5, primary versus secondary storage. The fundamental difference between primary and secondary storage really comes down to the ultimate hardware trade-off. You literally have to trade massive capacity for blazing speed, and vice versa. Primary storage is lightning fast purely because it speaks directly to the CPU, but it's physically smaller and, again, loses all its data when the power dies. Secondary storage is the exact opposite. It's not directly accessed by the CPU at all. The data has to get funneled through slower input-output channels. But the massive upside is that it can hold incredible terabytes of data, and most importantly, it stores all of that data permanently, with zero power required. And you interact with secondary storage every single day. It's your computer's main hard disk drive or solid-state drive. It's the little USB flash drive sitting on your keychain, or even the optical CDs and DVDs you might still have stashed in a desk drawer somewhere. We've seen how primary storage devices like RAM and cache act as that fast, active working desk. In total contrast, secondary storage is the massive, permanent, off-site warehouse where you file absolutely everything away for long-term safekeeping. Now, here's a fun question. What happens if you open up way too many browser tabs and completely max out your primary RAM working desk? Without a backup plan, your whole computer would just crash. But enter virtual memory. This is a genuinely brilliant software trick where your operating system actually borrows a chunk of space from your secondary hard drive to act as a temporary overflow zone, usually called a paging file. The OS basically juggles data back and forth between the RAM and the hard drive to keep the plate spinning. Now, it's way slower than real RAM, which is exactly why your computer starts to lag heavy when it runs out of memory, but it absolutely saves your system from completely freezing up. Let's pull everything we've just learned together by tracking a single piece of data as it climbs up the hardware hierarchy. When you double-click a file, it starts way down in the permanent, slow warehouse of your secondary storage. From there, it gets loaded up into the faster, temporary workspace of primary RAM. And as the CPU starts crunching the numbers, the absolute most critical pieces of that data get bumped up into the hyper-fast cache memory sitting right next to the processor. Finally, it enters the CPU itself for execution. We're going to leave you with a thought to ponder. We've just spent this time outlining a very clear, strict hierarchy of memory. But as technology continues to race forward, solid-state drives are becoming phenomenally fast. We've been starting to see flash memory being used as an additional cache layer right on disk controllers just to bridge that latency gap. So as our permanent storage gets faster and our temporary memory grows ever larger, will the strict historical boundary between primary and secondary storage eventually just blur into one totally unified memory system? It's a deeply fascinating question for the future of computing hardware. Thank you so much for joining us for this explainer. We really hope you walk away with a much clearer picture of exactly what is going on under the hood of your machine.